Hello, everyone. I guess let's get started. My name is Chris Trezzo, and this is Sanjin Lee. We're both developers on the Hadoop team at Twitter, and we're here to talk about a new Yarn feature that we implemented called the Yarn Sharecash. So the agenda for today, this seems to be a different version of the slides. But okay, we're going to talk about give a sort of review of Yarn localization, go over an overview of the shared cache design, talk about adding resources to the cache, talk about cleaning up resources, also give some results that we got from our production clusters at Twitter, go over some anti-patterns and some dev tips and admin tips. So first, let's talk about localization as it stands in Yarn. This is a basic diagram of a Yarn cluster. You have the Yarn client, resource manager, 4 node managers, and a Hadoop distributed file system. So the first step is the Yarn client uploads resources to HDFS, or a well-known location that the node managers are all aware of. So in MapReduce, for example, it's a staging directory by default. It then submits an application to the resource manager. The resource manager schedules the containers on the node managers, and the node managers launch the containers, and as part of the container launch process, it copies the resources it needs to run from the distributed file system to the local disk on the node managers. So what happens if we need to run the same job a second time? Unfortunately, you'd have to copy the same resources multiple times, both from the Yarn client to HDFS, and then from HDFS to the individual node managers. Luckily, Yarn developers have thought about this, and they've introduced the Yarn local cache to take advantage, to alleviate the duplicate copying that would occur between the distributed file system and the node managers. So the Yarn local cache essentially caches local resources on the node manager's local disk. It maintains a target size, so let's say 65 gigabytes versus using a least recently used eviction policy, or yeah. And basically has 3 resource visibilities, public, user, and application. Public is basically visible and usable by everybody. User is visible by the same applications that are run by the same user, and application level visibility is only visible by the same application. And resources are identified in the local cache based on their HDFS file system path. So this is sort of important to note because they're not identified based on the contents of the file, but specifically by the location in HDFS. So if a file changes after a resource is localized and another resource is sharing that publicly localized file, it won't relocalize the file. So that introduces some interesting staleness situations that could occur if you're using shared resources. So now we've covered one case of redundant copying. The other case is from the Yarn client to the HDFS cluster. And currently, Yarn leaves that actually up to Yarn application developers. So for example, in MapReduce case, we have the distributed cache. So the distributed cache basically caches MapReduce job resources in HDFS. You can think of it as an API for retrieving known passing in HDFS. And the distributed cache and MapReduce application automatically add resources that are in the distributed cache to the Yarn local cache and set visibilities based on HDFS file permissions. So if you're using the default job submitter, it'll either set the visibility of your resources to either public or application level visibilities in the Yarn cache, depending upon the file permissions in HDFS. Some things to note, though, is that for when you're trying to share resources between applications, the MapReduce distributed cache does not manage the location of the resources in HDFS, or when to delete resources because they're no longer needed, or notifying you when the contents of a specific path has changed. So all of that is actually left up to the MapReduce end user to sort of deal with on their own. Basically the key points are that, in practice, even though we have these facilities for resource sharing, it actually doesn't happen that much between applications due to the amount of coordination that's required between applications, and also the fact that the default visibility for Yarn, by default, resources get uploaded to the staging directory, and the default visibility is then application level. So, and at least that's what we see on our production clusters. So here's some data that we collected from one of our clusters. On the y-axis, we have basically the number of jobs, and the x-axis is the amount of the size of the resources that they uploaded. So we have over 2 million jobs that basically upload from 100 megabytes to 200 megabytes of data, with the average size being around 128 megabytes. So if we go back to our diagram and the problem space between the Yarn client and HDFS, that's basically 125 megabytes per app times over 2 million apps that are uploading to HDFS, potentially redundantly. And then from the distributed file system to the node manager, we have basically, if we assume 1.7 containers launched per minute per node, you get a rate of 200 kilobytes per second per node of data that's transferred between HDFS and the node managers during localization. So we felt that these numbers were big enough to where we wanted to address this problem, and the way we went about addressing it is the Yarn shared cache. So there's a Jira and open source for this. It's Yarn 1492. It's currently been in production for around a year at Twitter, with hundreds of thousands of applications using it a day. Mostly, pretty much all actually MapReduce jobs, either using scalding and cascading. And we're currently working towards open sourcing this. Most of the feature, the Yarn feature is in 2.7 as a beta release, and then full MapReduce support is going to come very shortly in an upcoming Yarn release. So some of the design goals we had when building this feature is we wanted it to be scalable. It should be able to accommodate a large number of cache entries, like on the order of thousands. It should have minimal load on the name node and the resource manager, and it should be able to handle spikes gracefully. It should be secure, and so when we say secure, it's more about, one, knowing that when the shared cache says that it has a resource, it actually exists, and two, that the resources are identified by their contents and not by the location in HDFS. So you have confidence that what you're actually using is what you think you're using. And we wanted it to be fault tolerant. So We want Yarn applications to be able to continue running without the shared cache, and we also want the shared cache to be able to tolerate restarts. So if it shuts down and comes back up, it either needs to recreate its state or persist its state. And lastly, we wanted to be transparent. So from a Yarn developer perspective, we don't want them to have to worry about where do I place resources in HDFS, do I need to clean up resources? All of that should just be handled by the shared cache. And then from the MapReduce job perspective, we didn't want existing MapReduce jobs to have to be rewritten at all to leverage the shared cache. It should just be a simple configuration change so that they can leverage the benefits of the shared cache. So now I can go over a brief overview of the design. There's basically 4 major components. There's the shared cache client, the shared cache manager, which is divided up into the cleaner and the store, the shared cache uploader, and the directory in HDFS. So the Yarn client is basically responsible for communicating with the shared cache manager. It has a simple use API, a public API with one method called use. It's responsible for computing the checksum of each individual resource, and then also communicating with the shared cache manager the app ID of the resource that it's claiming, so that the shared cache manager knows which applications are actually using a given resource. Basically, when it talks to the shared cache manager, the manager will return the path to the resource in the cache if it exists, or null if it doesn't exist in the cache. The shared cache manager basically serves the requests from the clients and manages all the resources in the cache, both the metadata and the actual resources that are persisted in the HDFS directory. So the store itself maintains the metadata, so this includes a list of all the resources, the applications that are using those resources, the last time they were used, basically information that is used to maintain the entries in the cache. The cleaner, the second part of the shared cache manager, is basically a service that periodically scans through all the entries in the cache and purges stale resources based on an eviction policy. So the actual HDFS directory is the thing that stores things in the cache. And it's globally readable, but an important part is that it's writable only by a trusted user. So ideally the user that the node manager is running as. It has a nested directory structure, which includes the checksum of each individual resource. And the actual depth of the nesting is configurable, so you can control the total number of files that exist in each directory. So, and lastly, the shared cache uploader service is basically responsible for adding things to the shared cache. So the cleaner and the shared cache uploader are actually the only 2 things that modify the HDFS directory. Basically, the shared cache is the uploader is responsible for verifying the checksum of the resource, adding it to the cache, and it's also important to note that this is all done asynchronously, so adding things to the cache is not on the critical path for starting up applications, and it's done in a best effort way. So if adding something to the cache fails, existing apps can continue running and it doesn't affect them. So now let's walk through a simple sort of version of adding a resource to the cache. So we start out by the shared cache client computing a checksum of the resource. And then the client sends a use notification to the shared cache manager with the checksum of the resource and the application ID. The manager responds back with the path to the resource in the cache if if it exists. And at this point, the application can safely use this resource because it knows it exists in the cache and it won't be removed while the application is running. If the cache manager responds back with null, the application knows that the resource actually doesn't exist in the cache. So at this point, it needs to make the resource available to all the node managers. It would follow sort of an existing process that you saw in the previous overview of localization. It would upload these resources to a known location, preferably in HDFS. After that, the shared cache manager submits the application to the resource manager, and it can actually indicate that it wants to add a specific resource to the cache via the local resource interface. At this point, the resource manager launches the containers or schedules the containers for launch on the node managers, and the node managers localize the resource and launch the containers. Then asynchronously, after the containers are launched, the node manager computes the checksum again. So the key part is that the checksum is computed by a trusted party, and then uploads the resource to the proper shared cache directory. After that, the node manager notifies the shared cache manager to let him know that a new entry has been added to the shared cache. And following use calls for that specific checksum will then respond back with the known path as opposed to null. So now just a little bit more information about the shared cache cleaner. It basically runs periodically and scans through all the entries in the cache and evicts resources basically on if both of two conditions hold. One, if the resource has exceeded the staleness period. So if there's been no application that's accessed that resource by default in 1 week, but that's configurable. And secondly, if there are no current live applications that are using that resource. So now Sanjin will take over and talk about some of our results.
Thanks, Chris. So we'd like to go over some of the actual findings that we had after running this Sharecash in our production environment for a while. So if you remember, the key point about the Sharecash is really being able to minimize or eliminate the overhead that the localization has to the overall network environment of your system. So we really wanted to understand if this really comes to fruition and we're really relieving the pressure on the network coming from the localization. So how about the front portion of this localization picture where Yarn clients upload resources to the HDFS over and over again? We enabled the shared cache on our ad hoc clusters first. It was last July, July 2014. And since then, in our estimate, we basically saved 276.7 terabytes of data going into the HDFS coming from the clients. Basically, this is that much data that didn't go on the network as a result of the shared cache. And similarly, on our production clusters, recurring jobs, we enabled it in September 2014. And similarly, we saved about 272 terabytes of data on the front side of this localization picture. And on the back side of things, where individual worker nodes localize all this data, let me show you some of the data before we enable the shared cache. So before we enable the shared cache, each job, on average, uploaded and localized roughly 12 resources per job and about 125 megabytes on average. And if you consider the ratio of number of containers per job that are landing on the same node, that ratio in our environment comes out to be roughly 2, meaning that there are about twice number of containers as number of unique jobs on any given worker node. So if you take that into consideration, then these numbers somewhat come down. If you look at the per container picture, that number comes out to be like about 6 resources per container and about 63 megabytes per container. That's basically how much we localized before we enabled the shared cache. So I want you to remember some of these numbers. So what happened after we enabled the shared cache? So after the shared cache, what happened is that each job now is uploading only about 0.16 resources. Basically, they're virtually doing nothing in terms of this. And that's about 1.7 megabytes of resource. And if you look at the per container number, that's basically 0.08 resources and 840 kilobytes per container launch. So one interesting thing that I observed is that I hopped onto a node, looked at 1 month worth of node manager logs, and I just scoured the logs to see how many localizations were happening. Basically, they were just happening so few and far between. And that's basically the sort of the shared cache at work. And the total summary is that we are saving the localization bandwidth usage by 99%, basically 2 orders of magnitude by our very conservative estimate. So you saw this picture earlier. So this is basically how we were using network regarding the localization on the front side and also on the back side. This is before we enabled the shared cache. And after we enabled it, this is basically what we have today. We were uploading 125 megabytes per app. That's now down to 1.7 megabytes. On the back side, it's basically come down to a trickle. We're using only 2 kilobytes per second per node. That's basically network bandwidth going towards the localization, which is now virtually nothing compared to other activities that are going on. So this turned out to be one of the bigger successes we had in terms of really making our network resources super efficient. And I'd like to share one interesting anecdote also. So we have a class of applications whose responsibility is just constantly launching MapReduce jobs over and over again. Basically, it's some kind of a MapReduce job orchestrator whose function is simply launching jobs to a cluster. Prior to the shared cache, this machine was suffering from chronic problems because it had to upload hundreds of megabytes of jars every time it launched any job. It was simply flooding the NIC card that it had. And it was constantly alarming, and we were just in a constant situation to try to regulate the speed and some way, trying to find some way to make it sort of fly just under the radar. But we were having a hard time. And then we basically decided to enable the shared cache on this application first. And this is when we enabled the shared cache. This graph is basically a time graph of that machine's network bandwidth usage. And as you can see, the moment we enabled the shared cache, the network bandwidth usage just dropped totally to the floor, and we never heard from that alarm since. So having talked to you about the benefits of the shared cache, we also observed some interesting things that may hurt the value and the effectiveness of the shared cache. And I think it would be pretty instructive to go over some of these, what we call the anti-patterns regarding the shared cache. So from the get-go, we realized that there can be a certain types of churn that can happen for the shared cache, and they were somewhat detrimental to how well the shared cache works. And the first type is basically the resource churn. And we identified basically 2 issues as the cause of these resource churn. So one type of this issue is actually, I'm going to talk about the second one first, is what we call fat jars. If you operated any size MapReduce cluster, you know that a lot of users simply put all their dependencies together and create a single large jar, job jar, and use that for your MapReduce jobs. While it's really convenient for users to use such fat jars, it sort of works kind of against the shared cache because now you have something that's really monolithic, and it contains all sorts of different fine-grained dependencies in it, and many of these things don't really change at all. But the moment you change one jar out of inside this fat jar, basically the whole fat jar changes as a different resource. So effectively kind of thwarts the value of the shared cache, because they're not going to get much value out of the reuse. So we identified fat jars as one source of kind of challenges that we need to address. And then we also noticed some interesting issues with some of our, say, basically Twitter-generated jars. The issue was, normally if you build a certain jar, sometimes you add things like a properties file within those jars. And within those properties file, sometimes you can embed things like timestamp, or your build machine, or build ID, and things like that. So these properties files can change pretty rapidly, even though the binaries haven't really changed. So what you end up getting as a result is that as part of this build process, you end up creating artificially different jars every time you build something, although the actual binaries don't really change. So it creates some kind of a churn on the sort of the source side of the thing. So we wanted to look at those issues as a challenge to the shared cache. So this is one pretty instructive graph that we came up with by analyzing our users' jobs. So if you look at this graph, the y-axis is basically the number of resources, and the x-axis is basically the hit count from the point of the shared cache. So basically for each resource, we know how many cache hits that particular resource had. So one way to think about it is, if you move to the right of this graph, those are the resources that are getting reused over and over and over again. So the higher the hit count, the better the reuse. And if you go to the left side of the graph, those are the resources that are not really getting reused, but that are getting deposited into the shared cache. So we can call that left region of this graph basically the region of high churn. These are the resources that get added to the shared cache, but used only a few times, and then basically it never gets used again. And these are basically the resources that I talked to you about, like build process changing these jars rapidly so that they don't really have a chance to get reused. And this big region on the right side is basically the region of low churn. And this is sort of the region of value in terms of the shared cache. Some of these resources are getting even like hundreds of thousands of hits, or like a million hits. These are really your very stable jars that don't really change. This is you're drawing the value for your shared cache from. And if you look at the content of these resources, these are your well-known third-party jars, your like Apache jars, your Guava jars, and things like that that are just keeping reused over here. So the idea is that if you analyze your landscape of your users' jobs, you want to encourage users to move their resources from the region of high churn to a region of low churn, and the value of the shared cache will go up even higher. I'd like to talk about the fat jar one more time. So now this graph is a little bit different view of the same type of distribution. Now we have the number of jobs in the y-axis, and the x-axis is basically how many resources there are in terms of number of jobs. So basically, for a given job, how many resources it contains, including the job jar and the lib jars. And if you look at that one dot over there, basically, that's a number of jobs that had only one resource for a given job. And those are your fat jars. And we also found out that in our ecosystem, we had still tons and tons of fat jars in our system. And this is basically where the shared cache doesn't probably add too much value. And if the user can change this, and the idea is then break down this fat jar and basically create a more fine-grained approach in terms of delivering your resources. That way you can maximize reuse in terms of the shared cache, and you get more value out of it. And then there's a second type of churn, and that is actually the Yarn local cache churn. Yarn local cache also comes with a fixed size, and that's configurable. And if this local cache size is too small, then what happens is that even if the source side of things is very stable, things that are localized in the local cache can keep churning out of the local cache, because basically your local cache will become full rapidly, and then it keeps having to evict entities out of the local cache. So sizing the local cache appropriate for your use is actually very important. And it's a key ingredient in success in using this. And then there are other things that are competing for the public cache. The shared cache obviously end up in the public cache, but there are other things that are also using the public cache. And if they keep adding to the public cache at a pretty fast clip, then basically your stable resources get churned out of the local cache. So that's something you might want to watch out for. So some of the tips for the operators of the shared cache are, obviously, avoid fat jars. If you can help and encourage users to break down their monolithic jars into fine-grained bundles, you'll get more value out of the shared cache. And number two, make your jars repeatable. We talked about this, build artifacts that may keep changing the jars artificially. You may want to address those issues if you want to get more values out of this. Set your local cache size appropriately. In our case, we found that the default size of the local cache was not big enough for us, so we ended up increasing it to 64 gigabytes per node. And also increase the public localizer thread pool size. So this may be one of the first use cases of heavy use of the public cache. So we quickly found out that the public localizer got busier, much, much busier than before. So we ended up increasing the localizer thread pool size to match the activity that was happening. And also you might want to, once you put this in production and start running the cleaner, you may want to check and monitor the cleaner activity and make sure that they are actually humming along and they're keeping the size of the shared cache at a reasonable size. So you want to check the cleaner-related configuration also. For your developers, so if you're developing a Yarn application, something other than MapReduce, and you want to take advantage of the shared cache, then you want to look at two things. We try to make it as easy as possible to use a shared cache. One thing is basically simply using the shared cache client API, and it really boils down to simply invoking the use API to check the presence of your resource up in the shared cache. And if it does not exist, all you need to do is basically using your application submission context to offer your resource for sharing to the shared cache. And the rest is taken care of by the shared cache itself. And if you're a regular MapReduce developer user, actually your job is the easiest. You don't really have to do anything. As long as the shared cache is enabled on the cluster side, all you need to do is simply setting your MapReduce shared cache setting to the right setting, just to enable it. And it'll simply start looking at your job jar and lib jars and start putting them up on the shared cache. And you will just simply leverage them from that point on. OK, at this point, I'm going to turn it over to Chris again.
Yeah, so I would just like to acknowledge everybody that worked on this project as well to get to it to where it is at this point. So Ming Ma on coding, Karthik Kambatla for shepherding it through and design reviews and getting it committed into open source, and then Vinod, Jason, and you, your contributions to the design review were great and extremely helpful. So with that, question and answers. Anybody have any questions? If you could walk up to one of the mics, actually, that'd be awesome. Or I can just repeat the question. Go ahead. Yeah, so the question was, is the shared cache manager a separate process? As of right now, it's a separate daemon, but in future work, we would like to make it also be able to run as an embedded in the resource manager. And then the uploader portion of the shared cache that's on the node manager, that's just part of the node manager as well. Go ahead. Yep. Yes, the question is, during the talk, we mostly talked about jars and libjars, but does it also work for normal files and archives? And the answer is yes. For MapReduce, it works for all the different MapReduce resource types, but this is also just a generic Yarn feature. So from the Yarn perspective, it's just a file. So it works with all types of files.
Yeah, so if I can add one more thing to it. So we tried really hard to separate this into two parts. One is Yarn generic portion of the feature, which is Yarn local cache. So as long as you have any file and you take advantage of localization, then you can use it. And then we basically MapReduce just built on top of the Yarn generic local cache, Sharecash.
Yeah, so the key part is this is a Yarn level feature. So for applications outside of MapReduce, you can totally take advantage of this feature. Yeah.
So for multi-tenancy, have you guys considered encrypting the resources in the cache?
That could definitely be a future work, but at this point, we're essentially just relying on HDFS file permissions to protect the writability of the resources in the cache. Yeah.
Okay.
Go ahead. Yeah, so the question was, how do you determine what the optimal local cache size is on your cluster? And so one of the ways that we did that is basically we have metrics around the size of the HDFS cluster, the HDFS cache, so the actual shared cache directory. And you can use that as sort of like a very rough proxy of what your working set size is for all the resources that are being localized on the cluster. And then at that point, you can basically adjust the size of your local cache accordingly. And ideally, you should have the sizes relatively similar to the logical size of your directory in HDFS compared to the actual local disk size on your node managers. So there's not a lot of thrashing churn in the local cache.
Right. So
if you want to.
Yeah. So basically, what Chris said is true. So basically, if you look at the size of the HDFS source, that really gives you a sort of first level indicator of your local cache size. So you can take that as sort of in the first order approximation of the right local cache size. But then if you want to delve really into it, you can even look at node managers and see how quickly they churn out stable resource. And that also gives you an idea how fast they're being churned out of the local cache. So that's another tip. So you're saying for the same size, if the number of files is much larger, would it actually have a different implication? Is that the question?
You have like 10 gigabytes, 10 terabytes of data.
Mm-hmm.
One situation you have 100,000 of HDFS files. Another one just like 500 HDFS files.
Yes, you'd probably want to set your maximum file count of the local cache to a size that would handle the amount of small files that you're putting into the local cache, but the major target sort of throttling mechanism of the local cache is the target size.
And also having a large number of files, I think, has some memory implication on the node manager as well.
Yeah.
So that one way or the other, I think you make sure you want to have the right fairly good number of files configured, maximum number of files configured for it, and also the size.
I have a question. So you mentioned about cascading intermediate files, pig files and all that. So when pig, hive, they put a lot of intermediate files of these, specifically when they do map side joins or merge joins, they distribute the index files, the small tables through distributed cache. So is there a way to specifically skip certain files saying, okay, skip these files through the shared cache and, you know?
Yeah, so you could right now you can specify it based on the type of the MapReduce resource. So you could say, include libjars and job jars, but exclude like files, for example. If the files are of type file, right? Like if it's a generic cached file. I don't know if
Yeah, so another, so the MapReduce support currently is built on top of the MapReduce client. So if you go through the job client, then you sort of get it out of the box. That's why you have things like job jar, libjars, and these notions. But for things like, for example, pig doesn't really use these to launch jobs. They use the distributed cache programmatically. So for them, they need to write some code to do this. But you can control this actually on a per resource basis. So you can say, I'm not going to share mine. So I'm going to say, for this resource, I'm not going to offer it to the shared cache. Then you basically set this flag to false. Then that particular resource will never be offered to the shared cache, and thereby no one is going to be able to share them.
Yeah,
does that answer?
That's a very good point. Like from the perspective of the Yarn layer, you can control that individually, right? So if you're not using the standard MapReduce job submitter, you can control them based on each individual resource. Again?
Cache directly, I have no way to control that.
Actually, if you use the distributed cache API, then you have total control over them, because basically they're all along the lines of individual resources. You basically have an array of attributes for each individual resource, so you can actually set them on a totally per resource basis.
Okay, thank you.
Just in case of normal job submitter, we just happen to choose big chunks like job jar, libjars as a way to control these, but there's no reason that we had to do it. It's just for simplicity. It was just for simplicity.
Okay, thank you.
I think
we're out of time now. We can have conversations outside. Thank you.